Alright, let's have a look and see if sound is coming in. I do hear myself. Now let's check for video footage. And that's also working. Okay, we are good to go then. Let's unplug the headphones. And let's get started. Oh, I knew there was something I forgot to prepare. Give me a second. Okay, there we go. Another late night stream. This time, couldn't fit it into the schedule any other way. But yeah, today we are starting a new topic. Let me see, is the backside of this filled? Yes, it is. Okay. I'll just start with a brand new sheet. Today, we're going to be starting a new topic, and it's a pretty quick topic. And once you get the hang of it, it's also a pretty easy topic, but getting there takes a while. Don't underestimate it. It's something that I could probably just cover all in one stream, but I won't do that because I just feel like it makes more sense to give students a little bit of time working with the stuff that I'm going to cover today before introducing some of the other equations that I'm saving for next time. It's just, once you have all the equations for this chapter, even though the equations are mostly simple ones, you'll be able to solve, oftentimes you'll be able to solve the same problem using different sets of equations, and that overabundance of choice tends to confuse students. So I would rather just limit your options for today and then open up the new options next time so that you kind of have a sense for what can be done just with what I'm going to show today and what actually requires the stuff that we'll see next time. But enough rambling from me. Let's get started. Simple harmonic motion, often just abbreviated SHM if you see that while browsing around on the internet. Simple harmonic motion. What is it? We've talked about motion with constant acceleration. We've talked about projectile motion. We've talked about uniform circular motion. And now one more type of motion. And that'll be it for Physics 1 and Physics C as far as types of motion are concerned. Simple harmonic motion. So, simple harmonic motion, the go-to examples that you will see are the motion of something moving back and forth while attached to a spring, a mass spring system. And then the other classic example, of course, is a pendulum. Do I have anything pendulum-like here? I guess I can just unwind the string of this yo-yo. This yo-yo has turned out to be quite the useful physics toy, and to think I originally bought it just to answer one question by one student. At least I'm getting my money's worth, but yeah, this, I guess because I'm shaking my hand, it's not the best example, but a pendulum would be, you just lift it by some angle and let it go and it just swings back and forth. And of course, because in real life we have air resistance and friction, this motion is going to stop, but in an ideal situation where there is no friction or air resistance or other resistive forces, the object would engage in what's known as simple harmonic motion. So basically, it's a type of motion that repeats. It's this sort of back and forth motion that repeats, and not all repeating motion is simple harmonic motion. For example, you might have a situation where there's a rubber ball, for example, that bounces back and forth between two walls. It hits this wall, bounces off of it, rolls over to this wall, bounces off of it, rolls back, goes back and forth and back and forth and back and forth, and that is not simple harmonic motion. It's, I guess we would call it recurring motion, maybe. That might be a good word for it, recurring motion, but it's not simple harmonic motion. Simple harmonic motion has a more specific definition. So for motion to be simple harmonic, we've got three conditions, or I guess you could condense them into two conditions, depending on how you want to think about it. But simple harmonic motion relies on the presence of something called a restoring force. Relies on the presence of something called a restoring force. A force that is always pointing opposite to where the object is relative to some sort of center position that we call the equilibrium position. So there's some sort of restoring force always pointing towards what we call an equilibrium position, and we will take a look at why it's called the equilibrium position in a bit. I mean, if you remember what it means for an object to be in equilibrium, that pretty much gives it away, if you remember from way back when we did force. But yeah, there must be a restoring force, and this restoring force has conditions. So the first condition for simple harmonic motion, as far as its restoring force is concerned, is that the magnitude of the restoring force is proportional. I guess I wrote the two a little too high up. Is proportional to displacement from the equilibrium position. Is proportional to displacement from the equilibrium position. That's one. And then condition two is that the restoring force must point in the opposite direction to the displacement. Direction of restoring force is always opposite to displacement. And that's displacement from the equilibrium position. I'm not going to write all that out, but that is what I mean by displacement here. And then the third condition is that energy must be conserved. If energy is leaving the system, that's no longer simple harmonic motion. We would call it damped motion, damped oscillations. If energy is being taken away from the system as it moves, and the opposite term, if you're adding energy to the system, that's what we would call forced oscillation. And I guess I'll spell that word since I haven't written it yet. Oscillation. For something to oscillate is for it to go back and forth, to repeatedly go back and forth. Anyway, energy must be conserved is the third condition for simple harmonic motion. You don't have to worry about damping and forcing all that much. You just need to recognize conceptually when it's happening, but you don't have to do any calculations with it. I mean, well, I don't think it would be hard to, given the right amount of information. I don't think it would be too hard. You might get possibly a situation with a damped or forced oscillation where you could calculate, the work done by the force and add or subtract it from the total mechanical energy and calculate what the new maximum speed is of the oscillating object or whatever the case may be. You might get something simple like that, but you won't have to worry about things that they often bring up in higher physics courses like damping factors or whatever. So we're not going to touch on that. So going back to the three conditions, the first two conditions can really be just condensed into a single condition. If you want, you can summarize them with a simple mathematical expression. Force restoring equals the negative sign fulfills condition 2, that the direction of the restoring force is always opposite to displacement. And then, of course, the displacement itself, delta x or just x or whatever you want to use for your displacement variable. And then the magnitude of the restoring force has to be proportional to the displacement. So multiply this by some constant. Let's call that constant... what can I use? Something that isn't already used for something that we've worked with a lot. R is taken, S is taken, L is taken, H is taken, M is definitely taken. O is just going to look like a 0, so that's no good. P is taken. You know what? Fine. Let's use the Greek alphabet. Beta times x, where beta is some constant. So this right here, restoring force equals negative something constant times displacement. This summarizes conditions 1 and 2, and then condition 3, or I guess condition 2 if you think of 1 and 2 as a single condition, is conservation of energy. Easy peasy. So this format might look familiar to some of you. You might recognize this from somewhere. You might recall Hooke's law. You might remember Hooke's law, which defines the force in an ideal spring. Real springs don't behave ideally, but we can approximate them as ideal. Hooke's law says that the spring force is equal to negative k, which is called the spring constant, times x, the displacement from the spring's natural length, the displacement from its equilibrium position. And normally I drop the negative sign because I'm usually just concerned with magnitude, and we'll probably do that a lot in this chapter anyway, so that's not likely to change from what we've done before. But yeah, any spring that obeys Hooke's law, sometimes called a Hookean spring, Hookean spring. As long as you're working with ideal springs or Hookean springs, you can get simple harmonic motion out of them, because those springs do create a force. If I were to draw the situation, so here's a block, and we'll say that the surface is frictionless, right? Energy needs to be conserved after all. So you've got a block, mass m, and it starts off over here. This is like the rest position. This is what we would call the equilibrium position. Some people call it x0, some people call it xeq, and some people are just satisfied with setting it to 0 without giving it a special name. Do what works for you, but I would at least give it some sort of subscript to indicate that it's the equilibrium x. And you take this, you either push it or you pull it, doesn't matter which of the two you do. You disturb it in some way and then let it go, and it'll start moving back and forth and back and forth and back and forth. In fact, I can actually demonstrate that using a PhET simulation. So let's have a look at this one. The masses and springs simulation from PhET. I do have it linked in the course plan. So if you go to the course plan and you open simple harmonic motion, the course plan is linked in the description in case you don't know how to get to it. If you scroll down to Unit 8, Simple Harmonic Motion, and go down to the spring simulation over here, and you should be good to go if you want to follow along. But yeah, I'll just open intro mode, and let's grab 250 grams and attach it here. And I'm going to go ahead and lift this thing a little bit above its equilibrium position and let it go. And oh, it goes so far down that it actually goes below the screen. How about that? But yeah, there you have it. You've got your simple harmonic motion. It keeps on bouncing back and forth between two extreme positions. When it reaches the highest or lowest position that it's able to reach, it momentarily stops before coming back towards whichever direction equilibrium is. When it's at the top, it comes back down. When it's at the bottom, it comes back up. That is pretty much enough to tell you that the direction of the restoring force is always opposite to the direction of displacement from equilibrium. And here, let's see, we have a toggle for gravity, and damping is set to 0, so I bet if we go into lab mode, we can actually, we can control the damping, and that will probably show us some more interesting stuff. I'm not going to worry about those graphs over there for now, but let me go ahead and take a look at the direction of the acceleration. That is also the direction of the force. And where is my... I guess there's my displacement vector. Okay, what's messing this up is that it's a vertical spring, and it's going to be a while before we talk about... There we go. That was the line I wanted. But yeah, it's going to be a while before we talk about why the equilibrium line is actually down here and not up where the unstretched spring was before I attached this thing. We'll talk about that later. Don't worry. They're not cheating or anything. There's a reason behind it, which we'll worry about later. Now, if I turn on damping, even if it's just a little bit, over time you see that the oscillations get smaller and smaller until they gradually come to a stop. This is just what we see in real life, right? If you look at, here's another example of something that engages in simple harmonic motion, a pendulum. You raise it a few degrees, it swings back and forth and back and forth and back and forth. And if I turn on damping, or what they called friction here, then over time, if you've ever been to a park, yeah, I know, kids these days, they definitely go out to parks, right? They're totally not staying at home playing Fortnite or whatever. But for those of you who have had the experience of using a swing at a park, this is your experience, right? Unless you force the oscillations, unless you, every cycle you kick off or have somebody push you to keep you going, what's going to happen is air resistance is going to gradually slow you down, and your oscillations get smaller and smaller and smaller until eventually it just comes to a stop. And this one is actually taking its sweet time. My goodness. Even at maximum friction, it's still swinging. Okay, there. Now it stopped. But yeah, there you go. Those are two classic cases of simple harmonic motion, which we will be studying for most of this chapter. Let me switch back to my document camera and try to remember what else I wanted to add here. There was something else I wanted to comment on. Oh, right. This over here. So this ball bouncing back and forth is not in simple harmonic motion because the force that pushes it back and forth isn't always present. It's only present during the brief moments that this object is in contact with either of the walls. But when the object is somewhere over here between the walls, there is no horizontal force on it. We can't have that. Also, it should be, the magnitude of the restoring force should be proportional to displacement from equilibrium. If we say that this is the equilibrium position over here, then clearly there's a period in between the walls where the object can have any displacement from this line and there's no change in the force on it until, again, it hits one of those walls. So it can go for a good amount of distance without experiencing any change in the force that's acting on it. So it just doesn't fit the requirements. It doesn't meet the definition of simple harmonic motion. And there's the basic definition out of the way. Now let me see what's next. So next up would just be energy. So we're going to focus on springs for now. We'll deal with the pendulum later. We'll just deal with springs for now, and let's just do an exercise or two that have us review how force and energy work in a spring. Let's just review how springs work. Force we already stated. Force in a spring is equal to negative kx. I'm usually going to drop the negative sign just for the sake of, simplicity. But energy is another thing that we learned. The potential energy in a spring, I call it spring potential energy, but textbooks will call it elastic potential energy because technically it's not just limited to springs. You can also have it in things like rubber bands and whatnot. But spring potential energy, elastic potential energy, whatever you want to call it, is equal to 1/2 kx squared, and this is something that is typically derived using calculus, although if I remember correctly, we did show how to do it without the need for calculus. We did look at a graph of force versus position and calculate the area under that graph. It was a simple triangle, so no actual calculus was needed there. But yeah, spring potential energy, 1/2 kx squared. If we remember this, then we should be good to go for some of the problems we're about to see. Before that, though, two things. So, the equilibrium position over here, it's called the equilibrium position because it is where the net force on the object is zero. The only forces that would act on this object are, well, normal force, which cancels out with the gravitational force, so those don't come into play here. And then we said the surface is frictionless, so the only force left is the spring force. So if the spring force is the net force, then yeah, it makes sense that the place where the spring force is zero, which is also where the net force is zero, would be called the equilibrium position. It's when the object is in static equilibrium. Very temporary static equilibrium, but static equilibrium nonetheless. So this is the point, the only point in this object's motion as it moves back and forth between, let me draw two lines over here. As this thing moves back and forth between those two blue lines, that middle red line is the only point where the acceleration is actually zero. Everywhere else there is going to be some non-zero acceleration of the object. So either the object will be over here on the left-hand side and its acceleration will be to the right, or it will be over here on the right-hand side and accelerating to the left. And sometimes that acceleration is going to be with the object's motion, sometimes it's going to be against the object's motion. Sometimes the object will be on its way to the right, and this acceleration over here to the left will be decelerating it, slowing it down. And other times it will have gotten here and then it's on its way back, and in that case its velocity is going with its acceleration, so it would be speeding up, speeding up, speeding up. Gets to here where the acceleration is zero, no more speeding up, and then once it goes past this point, what happens? Well, now it's going against acceleration in the opposite direction on the left-hand side. So if we start at the equilibrium position, go right, slow down, slow down, slow down, slow down, turn back left, speed up, speed up, speed up, speed up, speed up, no more acceleration, slow down, slow down, slow down. So if we're speeding up until we hit the equilibrium position and then we start slowing down after, if our speed is going up, if I were to graph speed versus position and mark my equilibrium position over here, then we are speeding up, speeding up, speeding up, speeding up as we approach the equilibrium position. Once we hit it and go past it, now we're slowing down, slowing down, slowing down, slowing down. This means that we achieve maximum speed at the equilibrium position. Equilibrium position is the position of maximum speed. Vmax occurs at x equilibrium, or x equals 0 if that's how you want to denote it. So maximum speed occurs at the equilibrium position. Perhaps that reasoning wasn't very convincing to you. Okay, we can look at it another way. We can look at it in terms of conservation of energy. When the object is at one of these two blue lines, that is the farthest it will stretch. That's what we might call x max, also known as capital A in textbooks. The capital A stands for amplitude. So that's another vocab word for you, amplitude. It's just the magnitude of the maximum displacement of an object in simple harmonic motion. So when the object is at either of these blue lines, that's as far as it'll go. If I yanked it this far and then let it go, then the amount of energy I put into the system is only enough that it can go all the way over to here, and that's where it'll stop. It can't go past this line any further to the left. It stops here, turns around, and then repeats the same thing over here, stops, can't go any farther than this, turns around, and over and over and over. It just repeats that same cycle. So these two positions are the farthest you can go from equilibrium. That means at those positions, that's where your spring potential energy is at its highest. So A, or X max, if you prefer to call it that, is the position of maximum potential energy, So we've got two positions where the potential energy is a maximum. We've got one position where the speed is a maximum. Whether it's to the right or to the left depends on which phase of the cycle you're in. It could be either or depending on when you look at it. Sometimes it'll be in this position heading to the right, sometimes it'll be in this position heading to the left. But either way, if it's in this position, it's moving at its fastest at that moment. And that would also mean then, if the speed is a maximum here, that would also mean that the kinetic energy, which depends on speed, is also a maximum there. So Vmax occurs at the equilibrium position, but also that's where kinetic energy is a maximum. That's also where kinetic energy is a maximum. And if we apply conservation of energy here, then we can see why this all makes sense. We can just further convince ourselves that all of this is true. So we said the normal force and the gravitational force cancel each other out, so no net force there. The only force left over, since there's no friction, is the spring force. And we said the spring force, as long as we're dealing with an ideal spring that obeys Hooke's law, is conservative. We said that way back in the energy chapter. At least I'm pretty sure we did, or else how did we get this far without knowing that? So spring potential energy is conservative, which means since no other forces are over here doing work, there's no net force doing work, the only force that does work is a conservative force, so the total non-conservative work is zero, which means change in mechanical energy is zero. So that tells me that 1/2 mv1 squared plus 1/2 k x1 squared is equal to, at some other point in time, 1/2 mv2 squared plus 1/2 k x2 squared. If I were to pick two arbitrary positions between, of course, the limits of where this mass actually bounces back and forth. If I were to pick two arbitrary locations, x1 and x2, then the velocities v1 and v2 could be related to each other through this equation. kinetic energy at position 1 plus potential energy at position 1 equals kinetic energy at position 2 plus potential energy at position 2 equals kinetic plus potential energy at position 3 equals kinetic plus potential energy at position 4, and so on and so forth. You could actually have as many equal signs as you wanted over here, technically. You could just keep this going. Not M3, the mass is constant, V3, and 1/2 K X3 squared, and so on and so forth. So we already know at these two positions, when x is equal to a, we already know that's where the potential energy is a maximum. Well, 1/2 mv squared plus 1/2 kx squared, that's equal to the total mechanical energy. All of these are equal to mechanical energy total. And since mechanical energy is conserved, that total must remain the same. So how do I maximize one of these types of energy versus the other? Well, it's simple. You just make that type of energy eat up the entire total and leave nothing behind for the other type of energy. So maximum potential energy is when all of the mechanical energy goes into potential energy and none of it goes into kinetic energy. So that would mean then that you would set the speed to 0. So when the speed is 0, that is where you get the maximum potential energy, which is going to be equal to 1/2 Ka squared. You could also do the opposite. Where do you have the greatest speed? Where does Vmax occur? If you weren't convinced by what I did over here, then you can just reason through it using energy here. So that would occur wherever kinetic energy is the highest, and kinetic energy is the highest when potential energy is the lowest. So that's going to be 1/2 mv max squared. That occurs when the potential energy is 0. And for that to happen, x would have to be 0. That's your equilibrium position as we've defined it. So it's very important to remember these three special positions and how the energy is divvied up at these positions. A lot of times students will forget that they have these options, but they are pretty useful. They can help you get out of some sticky algebraic situations. You'll have problems where I'm not sure how to describe them off the top of my head, but you'll have problems where you might be given information about, position and displacement, and you're trying to get something in terms of the maximum speed, and you're just kind of tearing your hair out trying to figure out what to do. And usually what's happening there, what you're getting stuck on, is you're forgetting that you can just convert 1/2 Ka squared is equal to 1/2 mv max squared. So you can write the potential energy in terms of kinetic energy, or vice versa, as needed. This will make more sense once we look at a problem or two that will force us to use this. So how about we actually go ahead and do that? Let's go ahead and look at some problems involving force and energy for an object oscillating while attached to a spring. what do we have? Oh, actually, this one might be exactly what I was looking for, exactly what I was talking about. So it says, a simple harmonic oscillator has a total energy of E, capital E. Part A says, determine the kinetic and potential energies when the displacement is 1/2 the amplitude. And then part B says, for what value of the displacement does the kinetic energy equal the potential energy? So those are the two things to find. Those are the two things to find. So it says total energy is E, mechanical energy total. They're just calling that big E. And then part A says determine the kinetic and potential energies when the displacement is 1/2 the amplitude. What are Ke and elastic potential energy? What are they when the displacement is 1/2 the amplitude? When x is equal to a over 2, or x max over 2 if that's how you prefer to write it. I usually try both. I don't know why I choose to call it x max in some situations and call it a in other situations, but I've used both, so there you go. If you don't think you can fully commit to one or the other, then you can be like me. You don't have to. You can just kind of feel your way through it and pick whatever feels appropriate for the situation. So what is the kinetic energy and elastic potential energy when x is equal to a over 2? Well, the total energy is equal to, at any given point, it's equal to 1/2 mv squared plus 1/2 kx squared. But the total energy is also equal to the maximum kinetic energy, and it's also equal to the maximum potential energy, 1/2 Ka squared. This is the part that a lot of students forget to use. This is the part that would probably end up simplifying this problem for you considerably. So I'm going to go ahead and plug in a over 2 for my x over here, and let's see what I get. I get energy equals 1/2 mv squared plus 1/2 k a over 2 squared. If I square the a over 2, then I get a squared over 4. So I get 1/4. I get 1/2 mv squared plus 1/4 of 1/2 Ka squared. There's a reason why I'm not multiplying the 1/4 and the 1/2 to get a 1/8. There's a reason for that. And the reason is because 1/2 Ka squared, what is that? That's equal to the total energy. So what we're really supposed to discover here is that when x is equal to a over 2, the potential energy is just 1/4 of the total, whatever that total would be, whatever that total may be. The potential energy at half the amplitude is 1/4 of that total, which then must mean that the kinetic energy is 3/4 of that total. So potential energy is equal to 1/4 of E. And since the total is E, that must mean that the kinetic energy is 3/4 of E. Pretty simple when you're watching somebody else doing it, but very easy to forget when you're doing it in the moment unless you practice a lot. That's the one issue with this chapter. The easy parts are deceptively easy to the point where students will neglect this chapter and not practice enough, and that's where it gets them. So make sure to practice with this chapter. It is super important. The questions are often simple, but the value is in the repetition. Without repetition, you're just going to be kind of flailing about without any sense of direction on what to do. So the homework that I actually have listed, I might as well show it off now before I forget to. The homework that I'm going to have is this simple harmonic motion worksheet over here. It's just a bunch of repeated exercises. It's just a bunch of repetition. The exercises aren't particularly hard, but what I like about this worksheet, and it's not mine by the way, I just found it online one time through a random Google search. What I like about this, ignore the fact that it's talking about concepts we haven't discussed yet, but what I like about it is that it gives you a lot of repetition. You need that repetition to just kind of make parts of the thought process a little bit more automatic in your brain. You can't afford to spend time overthinking these problems. It will cost you a lot of time, and the more time it costs you, the more anxious you will get, and that just, then you have the double whammy. You're running low on time and you're anxious, and that's making you waste even more time, which makes you even more anxious, and yeah, that downward spiral, let's not get into that. Also, it's got an answer key, so be sure to check your work there. Anyway, back to my document camera. So we just answered part A of this question. Part B says, for what value of the displacement does the kinetic energy equal the potential energy? Well, clearly it's not at half the amplitude. That's what some people would first guess. Some people would first guess, oh, well, the halfway point must be where the kinetic and potential energy are split evenly, right? Wrong. We can already see it's uneven. It's 1/4 for the potential energy and 3/4 of the total for the kinetic energy. So we need someplace a little farther out than halfway in order for there to be more potential energy. So here's what we can do. Again, take advantage of the fact that the total mechanical energy can be rewritten as 1/2 mv max squared or 1/2 Ka squared. I think I'm just going to use 1/2 Ka squared here, since they were asking for a displacement. For what value of the displacement does the kinetic energy equal the potential energy? So yeah, I'm going to use that. So I'm going to do energy total, which equals 1/2 Ka squared is what I'm going to use, equals 1/2 mv squared plus 1/2 kx squared, where these two are equal to each other. Well, if I'm doing it where these two are equal to each other, then I can either replace 1/2 kx squared with another copy of this 1/2 mv squared, or I could do the opposite. I could replace 1/2 mv squared with 1/2 kx squared. We're looking for the position where these are equal, after all. That's the condition that is given to us by part B. This is our condition that we're trying to solve for. Not an equation that's always true. Be very careful here. I'm not stating this as some universal truth. This is just a condition that we are given, a specific moment in time for this object's oscillation where this is true. It's not true anywhere else. We're trying to find where that is true. Do not take it as some sort of universal statement. So I'm going to go ahead and replace the 1/2 mv squared with 1/2 kx squared using this substitution. And that'll give me 1/2 kx squared plus 1/2 kx squared is 1 kx squared. So total energy, which is 1/2 ka squared, equals kx squared. The k's cancel out. And now I've got a squared over 2 equals x squared. If I take the square root on both sides, I get x equals the square root of a squared is a over the square root of 2 is, well, the square root of 2. And you don't have to rationalize the denominator or any of that nonsense that your pre-calculus teacher made you do. I mean, I know why they make you do it. It's to make you practice rationalizing denominators in case you ever need to do it after pre-calc. But in case some of you are left with the impression that it's just a thing that you have to do, no, it's not. Far from it. It's just what I like to call a teacher semantic. So yeah, when the object is at amplitude over square root 2, I guess let me type in 1 over square root 2 and see what that is. I think it would be what, like 0.7 something? 1 over square root 2. Whoops, wrong button. 1 divided by square root of 2. Yeah, 0.7071. Which is equal to sine or cosine of 45 degrees. Fun fact for you there. So yeah, 0.7071. So somewhere at about 70% of the amplitude. Somewhere at around a little more than 2/3 of the way. Somewhere around here is actually where the kinetic energy and potential energy are equal. Not halfway between the red line and the blue line. Not what you would first think. Be very careful. Do not be tempted by those mental shortcuts. I would hope by this point in physics you have learned that physics has a lot of counterintuitive results, and you probably shouldn't just trust your first guess on some things without doing the math first. But there we go. That was an exercise in remembering that total energy can be set to the maximum kinetic energy or the maximum potential energy in order to make some mathematical simplifications when needed. Let's have a look at another problem. Okay, here's a classic. And by classic, I mean I give it to my students every single year. It says a 0.4 kilogram object. So mass is 0.4 kilograms. Is connected to a light spring with a force constant of 19.6 newtons per meter. So force constant, spring constant, is 19.6 newtons per meter. Well, that is 2 times G, which is probably not a coincidence. It oscillates on a frictionless horizontal surface, so we don't have to worry about damping or forcing. If the spring is compressed 4 centimeters and released from rest, so they had a spring with an object attached to it, they compressed it 4 centimeters and let it go. This one doesn't compress very far, so maybe I'd be better off stretching it 4 centimeters and letting it go. But you get the idea. By compressing it or stretching it a certain amount from rest and then letting it go, that's you setting the amplitude. Whatever you stretch or compress it to before letting it go, that's going to be the amplitude, or X max. So if the spring is compressed 4 centimeters and released from rest, determine the maximum speed of the object, the speed of the object when the spring is compressed 1.5 centimeters, the speed of the object when the spring is stretched 1.5 centimeters, and for what value of x does the speed equal 1/2 the maximum speed. Okay, if the spring is compressed 4 centimeters and released from rest, so amplitude equals 4 centimeters, or if you prefer, 0.04 when converted to meters. Do we actually need to convert it to meters here? Well, yeah, because K is in newtons per meter, so yeah, amplitude would need to be in meters in order to get units that aren't confusing. So determine the maximum speed of the object. That is our first task. What is Vmax? Okay, well, easy enough. We can just compare 2 points in this object's oscillation. I guess we can go ahead and draw the same drawing that we had on the back side of the page. We've got mass m, and it oscillates between 2 positions that are each 4 centimeters away from this central equilibrium position. So that's 4 centimeters one way, that's 4 centimeters the other way. And we're trying to find Vmax, so we can compare any 2 positions we want between that furthest left dotted line and the one that I drew furthest to the right. We can compare any 2 positions we want, but of course some choices are smarter than others. The smartest choices would be to compare either of the ends with the central or equilibrium position. So I'm going to do set when the potential energy is a maximum, 1/2 Ka squared. I'm going to compare that position, 1/2 Ka squared plus 0 kinetic energy. I'm going to compare that to the position where there's 0 potential energy and it's all kinetic energy, in which case the speed is Vmax. How about that? And the 1/2 cancels out, of course. and just divide by m and take the square root. K a squared over m, all under a square root, is equal to V max. Technically it's a plus or minus because it could be going to the left or to the right at any given moment in time. We would actually have to figure out when it started moving and which way it was going and where it was when it started moving in order to know for sure whether we see it moving to the left or to the right. But we'll just focus on magnitude here. So this works nicely for us because we know A. We know A is 0.04, so we can plug that in here. We know K is 19.6, and we know M is 0.4. So the rest is just plugging in numbers in the calculator. I would skip this, but it's easy enough to do, so let's go ahead and see what number we're supposed to get. So those of you who are following along at home can compare results and make sure you did it right. 19.6 times 0.04 squared divided by 0.4, all under the square root, and I'm getting exactly 0.28. How about that? Not an ugly, endless string of decimals. We get V max equals 0.28, and that should be in meters per second. That is part A. Let me get a sip of water before rereading part B. Okay, part B. Said, what's the speed of the object when the spring is compressed 1.5 centimeters? Well, that's not going to be at either of the extremes, so unfortunately I can't pick one of the positions where one of the energies is 0 anymore. I'm actually going to have to say total energy of the system is equal to 1/2 mv squared at that position plus 1/2 k that position squared equals the total mechanical energy, which can be set to, again, the mechanical energy at any other point between this left bound and this right bound. So I will pick what? I guess it doesn't really matter here since I have all the numbers, but I think I'll just pick the central position. I'll set it equal to the mechanical energy at the equilibrium position, which is 0, potential energy plus 1/2 mv max squared. And now that I've written that, I'm realizing that I'm not being consistent with the order in which I'm writing my energies. Here I wrote kinetic before potential, and here I did potential before kinetic, but that shouldn't bother anybody too much, I would hope. I would hope by this point in the course something like that doesn't bother us and our math skills have sharpened to the point where this isn't going to confuse us too much. We can cancel the 1/2 everywhere. I guess this would require reusing the Vmax that we got earlier, which would be one point against using this, is that it's reusing a calculated result and carries the risk of, if that calculation from earlier is wrong, then this next calculation will also be wrong. So maybe from a risk management perspective, I should have actually chosen one of the ends. But it's okay. I'm pretty confident that this is correct because, like I said, this is a classic that I give to my students every year, and I vaguely remember getting this result. It does look familiar to me is what I'm saying. So I'm pretty confident that I've done it right, unless I've just been doing it wrong for the past 10 years. Okay, and we were calculating what again? We were calculating V. So subtract kx squared and divide by m. I'll do that in two separate steps. So mv squared equals mv max squared minus kx squared. And then if I divide by m, v squared equals v max squared minus k over m x squared. And then take the square root on both sides. So v max squared, that's 0.28 squared, minus k was 19.6 over m was 0.4 times x squared. X was 1.5 centimeters is what the problem said. The problem said x equals 1.5 centimeters, which is about here, or perhaps here, depending on which side we're talking about. I have no way of knowing for sure from the wording of this problem. It could be either. Not that it's going to matter, because we're going to square the 1.5 centimeters no matter what. So it doesn't matter if it's in the positive or negative direction. So 0.015 squared. So I've got 0.28 squared minus 19.6 over 0.4 times 0.015 squared. And I'm getting v squared equals 0.067375. V squared equals 0.067375. If I take the square root of that, I get about 0.2595669. I'll just round that to 0.260. I'll say V is approximately 0.260 meters per second. Does this result make sense? Well, it's less than 0.28, which is good. It's less than the maximum. If we got something more than the maximum, that would be cause for concern. So at least it's less than the maximum we calculated. That's one point of reassurance. Part C says, find the speed of the object when the spring is stretched 1.5 centimeters. So one was when it was compressed 1.5 centimeters. The other is when it's stretched 1.5 centimeters. That's a trick question. It should be the same either way. The magnitude of the spring force and the potential energy in it do not depend on whether it was a stretch or a compression. They don't depend on the direction of the displacement, only how much displacement was done. So 1.5 centimeters to one side versus the other should give you the same results, should give you the same V. All right. And then part D says, for what value of x does the speed equal 1/2 the maximum speed? Okay, so this is similar to the previous problem, actually. This is just more of what we did in the previous problem. For what value of x does the speed equal 1/2 the maximum speed? equals question mark when V equals V max over 2. What is it going to be? For this, we don't even need any of the numbers they gave us. We can just give some sort of general formula. So the total mechanical energy total, we can set it equal to all potential energy. We can put all of it into potential energy and call it 1/2 Ka squared, or we can put it all into kinetic energy and call it 1/2 mv max squared, or we can have it shared perhaps evenly, perhaps not so evenly between the two. 1/2 K x squared plus 1/2 mv squared. Okay, they said that V is equal to V max over 2, so we can make that substitution here, and we should get something very similar to what we got earlier. So 1/2 K, x squared, 1/2 K x squared plus, let's see, V gets replaced with V max over 2, and if I square that, that's V max squared over 4, so I'm going to have a 1/4 times 1/2 mv max squared. That is 1/4 of the total mechanical energy, right? The total mechanical energy is equal to 1/2 mv max squared. So if this is 1/4 of the total, then this 1/2 kx squared is equal to 3/4 of the total. So 1/2 kx squared equals 3/4 of mechanical energy total, which also means it's equal to 3/4 of, well, mechanical energy total can be also written as 1/2 Ka squared. Okay, 3/4 of 1/2 Ka squared versus 1/2 Kx squared is now what we're comparing. 1/2 Kx squared equals 3/4 of 1/2 Ka squared. The 1/2 K and the 1/2 K cancel out. So we're left with 3a squared over 4 equals x squared. So it's going to be that x equals the square root of that. That's going to be square root of 3 over square root of 4 is 2 times square root of a squared is a. So there you go. At x equals, I guess I would also put plus or minus, right? Because it can be in either direction. And that does it for that problem. I'm looking for something that actually involves force, because we haven't done that yet. I didn't expect I'd be yawning so much. Maybe this was actually too late to start a physics session, but in for a penny, in for a pound. Here's hoping there aren't too many terrible mistakes that I catch when reviewing this later. I still have to review and timestamp the previous stream as well. I'll probably be doing that tomorrow. I guess, no, to do that we would need to discuss vertical springs, which we haven't done yet. Yeah, let's not do that one yet. Find a simpler one. I don't seem to have one here. Let me see. I mean, that one might be a bit too simple. Okay, I'm probably thinking of a problem in the other book is why I might not be finding it. Let me open the other book and check. Because I know there's something in one of my books that matches what I'm looking for. Okay, we're here now. Okay, this one. So it says, wait a minute, no, that's also a vertical spring problem. That's also a vertical spring problem. No good. Was it really not in this book? Let me double check. I know I had it in one of these things, but where? Okay, here we go. Here's something. Finally found one. So it says a load of 50 newtons attached to a spring hanging vertically stretches the spring 5 centimeters. So we have a spring that gets stretched by 5 centimeters when a 50 newton load is attached to it. When a load of weight 50 newtons is attached to it, it stretches by they said 5 centimeters. The spring is now placed horizontally on a table and stretched 11 centimeters. So they take that same spring and lay it out horizontally, and now they stretch it 11 centimeters. So let's say its equilibrium position was over here, and we'll say this is 11 centimeters. Actually, that means there's not enough wall for it to actually oscillate. It'll hit the wall before it manages to complete a single cycle. But let's not take my drawing to scale. How about that? What force is required to stretch the spring by this amount, this 11 centimeters? So it's asking what the force is, and then it's asking plot a graph of force on the y-axis versus spring displacement from the equilibrium position along the x-axis. They could have said vertical and horizontal axes instead. Saying on the y-axis and x-axis here might be confusing. But yeah, the graph it's just going to be a linear graph. I don't see why they would even have us bother doing this, but okay. So first we need to figure out what the spring constant is. So this is different from what I did earlier in the PhET simulation. In the PhET simulation, what I did was I attached a block and I let it go. I let it go after attaching it here, and the block just kind of dragged it down past this balancing point, this equilibrium position, if you will, the place where the net force on the block is 0 and it stays at rest, if it was at rest to begin with at least. So instead of doing that, what I did in the PhET simulation was I attached a block over here and I let it go. And what that does is, well, the force of gravity is greater than the spring force upward, which starts off as 0. So the object gets carried down, builds up some downward velocity. By the time it hits this position where the net force is 0, well, it's already got velocity downward, so if there's no acceleration to slow it down, then it's just going to keep going down. And that's what we saw happening. It kept going down, and then some spring force started building up and eventually yanks it back up. And then it starts bobbing up and down and up and down, as you would expect in this chapter, as you would expect of a simple harmonic oscillator. So yeah, be very careful about that. In my experience, they don't do a very good job wording it super clearly and being careful with how they word it to make it abundantly clear, whether it's hang and let go versus hang and gently let down until equilibrium is reached. But you might develop a feel for it as you see more and more of these problems. Anyway, this is a attach and let down gently sort of situation. So we know at this point the spring force upward must be canceling with the gravitational force downward. So we can say K times the 5 centimeters is 0.05 meters. Kx is equal in magnitude to 50 newtons. So divide by 0.05 and you're done. That's the same as multiplying by 20. So K equals 1,000. K is 1,000 newtons per meter. I was about to say just newtons. That would have been bad. Brain malfunction averted. So now we know the spring constant. It says what force is required to stretch the spring by 11 centimeters now that it's being laid out horizontally. Well, the spring constant isn't going to change just because you change the orientation of the spring. It's a property of the spring. It has to do with the stiffness or rigidness of the spring, how much it's willing to stretch and how much force it takes to stretch it. So all we need to do now is just take K and multiply it by 11 centimeters and we're done. K times 11 centimeters, that's 1,000 times 0.11 if you convert the 11 centimeters to meters, and that gives you 110. That gives you 110 newtons over here. Spring force here is 110 newtons. So that's part A. Part B was asking plot a graph of force versus spring displacement. I don't know if they meant magnitude of force or take magnitude and direction, but force versus position. So it's going to be a linear graph. And I guess if you start at position 0, the force would be 0. And it'll go up or down from there depending on whether you would interpret this force as being a negative or a positive. But either way, either this or this, pick one. Pick an interpretation, and if you're not sure and you have the opportunity to ask the person who is going to be grading your stuff what they wanted, how they wanted you to interpret this, as long as you ask them for clarification, you should be fine. But yeah, it's one of those two, force versus position. So it was saying just plot a graph of force. Yeah, there you go. I gave basically two graphs. Okay. I think we are ready to talk about our next thing, which is vertical springs. Let's talk vertical springs. So it turns out that we can treat a vertical spring as behaving exactly like a horizontal spring if we make a simple adjustment. And that simple adjustment is, instead of measuring the equilibrium position from its original length, where it reached with its original length, instead we define a new equilibrium position based on, well, where the gravitational force and the spring force cancel each other out and are in equilibrium. It's almost as if it's called an equilibrium position. That was sarcasm, by the way. That's kind of literally the reason why it's called the equilibrium position. So, let me see, how do I want to do this? I'm basically going to redraw this scenario over here. So I've got this unstretched spring, and then I have it stretched a bit. After some mass is attached to it, and then after the mass is attached to it, I stretch it even further and let it go, and it starts bouncing up and down and up and down, as one would expect. in simple harmonic motion. So basically, what I can do, what we're going to discover here, is that the why am I blanking on this? The gravitational potential energy is a factor that we can eliminate and treat it exactly like this horizontal situation where gravitational potential energy doesn't factor into the energy at all. We can actually do that by making an adjustment to the equilibrium position. So here's what I am going to do. So this is the original equilibrium position over here at the top. And then from here to here, is what? Well, this point over here, I can figure out how far it is from here by simply doing, this is the point where kx, or I guess in this case ky, if we want to be pedantic about it, is equal to mg. Right? This is the new equilibrium position. This is where the forces down and the forces up must cancel out, so their magnitudes must be equal. So from this I can actually solve for y. I would just divide by k, and y, I guess I would call it y equilibrium equals mg over y. So this over here is a distance of mg over y. Okay. So now what I'm going to do is I'm going to say this is also going to be the position where the kinetic energy is a maximum. And if I pull this thing, I pull it down further from here and then let it go. I let it oscillate. Then I basically have two different displacements I could use. I could use this, or I could use the displacement from the original equilibrium position all the way up here. So I guess we will call them, what do we want to call them? I'll call this one A, and I'll call this one B. And let's go ahead and see what we can do with this. So B minus A is equal to this difference, mg over y. That's something worth noting. Let me wall off this problem so it doesn't get mixed up with the rest of our stuff. B minus A is equal to mg over y. So I want to do, just using the original equilibrium position over here, I want to try and set up my mechanical energy conservation equation. I'm going to say elastic potential energy up here. I'm going to compare this position with this bottom position. And I'm going to say 0 elastic potential energy plus, oh, actually wait, would that even work? I don't know anything about the kinetic energy at that point. Yeah, I don't think that would work. Hold on. I'm having a brain malfunction moment. I can feel it. Let's think here. So what am I trying to do here? There's some unknown kinetic energy when you're up here. This thing is going to go down over here. It's going to be let go. It's going to oscillate back and forth, and it's going to have some unknown kinetic energy up here. Whatever it is, I'll just call it 1/2 mv squared. So 1/2 mv squared up in this top dotted line plus 0 elastic potential energy plus mgh plus mg, where's h? I'm going to set my h equals 0 line to over here. That's going to be my h equals 0 line for gravitational potential energy. So my mgh over here, this is a distance of b above my 0 line, so that's going to be mgb. So that's the total energy over here. Equals, I want to set it equal to the what do I want to set it equal to? I want to set it equal to the total energy. Let's set it equal to the total energy down here. So that's going to be, well, down here, it's about to be let go and go straight up, which means it's at rest. So there would be 0 kinetic energy plus the elastic potential energy would be 1/2 k times, measuring from here, b squared, k times b squared, plus the gravitational potential energy here, well, we've set it to 0. Okay, let's see what we can do with this. So we said b minus a is equal to mg over y. So I can actually rewrite this. As b equals a plus mg over y. I even practiced this earlier today to make sure I would get it right. What am I missing here? Let me go ahead and make my substitutions and see. So 1/2 mv squared is going to be equal to 1/2 kb squared minus mgb. 1/2 kb squared minus mgb. If I replace the b with a plus mg over y, then this is equal to 1/2 k a plus mg over y squared minus mg times b, which is mg over y. Let me switch to this light blue. Wall this off. Okay, so my 1/2 mv squared is equal to, if I go ahead and FOIL this, I'm going to have 1/2 k a squared plus 2 mga over y Wait, what? I knew something was off. K. Y equilibrium equals mg over k. Why did I write y over here? Well, at least I caught it before finalizing the recording. I knew something was off. Okay, there we go. That looks much better. So where were we? 1/2 k, I was foiling this, so a plus mg over k. Well, oh, and I forgot that one too. Okay, now I think I've corrected all of them. Okay, 1/2 k times this stuff foiled, so a squared plus 2mga over k plus, it'll just be mg squared over k squared, all that in the parentheses, minus, this is going to be mg times mg, which is just mg squared over k, so that's minus mg in parentheses squared over k. I'm going to need to continue this on a new sheet. So we have 1/2 mv squared equals, if I distribute, I probably should have given myself more space here, but it's okay, equals 1/2 ka squared plus 1/2 k times, well, the 1/2 k and the 2 over k over here is going to cancel out, so that's just going to be plus mga. Right, the 1/2 cancels with the 2 and the k with the k. And then plus 1/2 k times mg squared over k squared. The k's reduce, so we would just have 1/2 and then mg squared over k, and then minus mg squared over k. Okay, 1/2 of this minus 1 of this is going to be negative 1/2, so 1/2 mv squared equals 1/2 ka squared plus mga minus mg squared over k. What can we do with this? I want to try and rewrite this in terms of y equilibrium, so one half mv squared equals, we'll keep the 1/2 ka squared over here, and then mg squared over k. I'm going to separate this into two mg's. So this is going to be plus mga minus mg over k. Okay, this should look familiar. Mg over k is equal to b minus a. Mg over k is equal to b minus a. I feel like I took a wrong turn somewhere and ended up taking more steps than I actually needed to, but I guess that's what I get for waiting until so late at night to do this. So mg over k is equal to b minus a, so this is going to be mgb minus mga. I feel like I'm just going around in circles at this point. So I'll get a 2mga minus mgb. How does that help in any way? Let me go and find the note card where I actually did this earlier today and see where did I go wrong with my previous calculations. Looking at it, is looking familiar, but I used different variables here, so that's making it a little bit harder to follow. Let's see, what can I do with what I have in front of me? Let me try and simplify this first before I take a look at my old notes. I mean, there is an alternative that I could give, which is a lot easier than what I'm doing here using energy. And I will probably end up resorting to that. Let me see. mga minus mgv would be mg times a minus b. No, that's not going to help us, is it? Let's see, mg over k. Mg over k is equal to this y equilibrium. So maybe I should do that. Maybe scrap this. Let's see, 1/2 mv squared equals 1/2 ka squared plus mga minus, this is going to be mg y equilibrium How does that help us? So A minus y equilibrium Yeah, I don't see anything meaningful in this. Maybe I'm just too tired to see it. Oh well, there's an easier proof, and I'll go back and redo this later. We'll just save the energy version of the proof for the next stream, because right now it's just not coming to me. I feel like I missed it somewhere along the way. I took a wrong turn, but I've got a quicker proof that we can do instead. So let's go back to scrap all this. Well, I'm not going to cross it out just in case I end up needing it next time. Let's do this. So you've got an unstretched spring over here, and then it gets stretched a little bit up until the spring force balances with the weight of some object, up until mg cancels out with ky. Or to be more specific, what I'm going to call y equilibrium. So this I'm calling y equilibrium, the new equilibrium position, compared to the old equilibrium position, which I guess I will call y0. And what happens now if I pull this thing down even further? And let it go. So this I would call a distance of, I guess I would call it a distance of just y from the new equilibrium position. Well then, what is the spring force acting on it over here? What is actually, better yet, what is the net force on this thing? So the net force on this thing would be a spring force of k times Well, the spring force would be measured starting from the original length of the spring, so it would be K times the distance from y0 to y equilibrium. I guess I would just call this 0. So it would be K times y equilibrium plus this extra y, right? This distance over here is YEQ. So we would have K times YEQ plus Y is the spring force upward, minus the gravitational force downward is still mg. So the net force on this thing when it's over here is gonna be, well, we already defined ky equilibrium as being equal to mg. We defined this y equilibrium position as being where ky is equal to mg. So if I distribute the k here, then I get ky equilibrium plus ky minus mg. These cancel out. So the net force acting on this thing is ky. The net force acting on this object when it's down here is equivalent to just a horizontal spring that was pulled by y meters from its rest position. If over here the net force starts at 0 and then you pull it y meters to the right, then there's going to be a net force on it of ky to the left. This is basically the same idea. If we start from here and we pull by y meters downward, then we have a net force upward of ky. It's basically this situation just rotated 90 degrees. I know that might not be the most convincing proof, but it at least gives you some faith that we can treat a vertical spring just like a horizontal spring by simply adjusting the equilibrium position, by treating it as if its actual equilibrium position is where the gravitational force cancels out with the spring force. If we treat this as the new equilibrium position and calculate all of our displacements from there, then we will get the exact same motion that we get from a horizontal spring that is given that same initial amplitude, that is stretched by that same amount. Okay, so there's that out of the way. Vertical versus horizontal springs, explained kind of poorly. I will revisit this next time once I can figure out what went wrong with the energy-based approach to the proof. I've done it multiple times before. I'm missing something. I missed something obvious along the way. Well, maybe it wasn't obvious. If it was, then I wouldn't have missed it. But it's okay. We'll deal with it next time. That's what That's what the second stream is for. That's another reason for splitting it into two streams instead of doing it all in one. Now, where did I want to go from here? So we just established that vertical springs can be treated as horizontal springs after making an adjustment to where you define your equilibrium position to be. And the reason I wanted to do that was to get us ready for a problem, which was what? Let me find it. Okay, I believe it's this one. So it says, at an outdoor market, a bunch of bananas is set into oscillatory motion with an amplitude of 20 centimeters on a spring with a force constant of 16 newtons per meter. So amplitude is 20 centimeters, or 0.2 if you convert it to meters. On a spring with a force constant of 16 newtons per meter. So K is equal to 16 newtons per meter. It is observed that the maximum speed of the bunch of bananas is 40 centimeters per second. Vmax equals 40 centimeters per second, which is also 0.4 if you convert it to meters per second. And the question is, what is the weight of the bananas in newtons? What is the weight of the bananas in newtons? I don't know why I circled that, but that is the big question that they're asking. So this is a vertical spring situation. We have a bunch of bananas. I guess I'll try and draw them actually banana shaped. Why not? There we go. We have a bunch of bananas. And it's oscillating up and down, back and forth. We'll say this is the equilibrium position. And it oscillates back and forth between that position and, let me do it in a different color, these two positions. And these distances are 0.2 meters each, so that's 0.2 meters. I didn't have enough room for that. And let me write 0.2 meters first, and that is also 0.2 meters of distance from this y equilibrium. So we need to find mg, and for that we need to figure out what? I guess we just need to find m. Okay, no need to overthink it. So we don't have to worry about the gravitational potential energy here. This is basically going to be the same as if the bunch of bananas was over here sliding on a frictionless surface while attached to the spring. It's basically equivalent to this situation. I know I haven't really proved it very convincingly today. We'll worry about that proof next time once I've had a chance to double check my work and see where I went wrong. But essentially we can treat it like this situation, where the only energies involved are kinetic and elastic potential energy. So we can just do total energy is mechanical energy total equals 1/2 mv squared plus 1/2 kx squared, or it's also equal to 1/2 mv max squared all on its own, or it's equal to 1/2 kx max squared, or a squared, all on its own. I'm going to use this and this over here because, well, they gave us Vmax and they gave us the amplitude. So that would allow us to immediately solve for m. I can say 1/2 Ka squared equals 1/2 mv max squared. The 1/2 and the 1/2 cancel out. I'm looking for m, so divide by Vmax squared. Ka squared over Vmax squared is equal to m. And if I plug in my numbers, what do I get? 16 times 0.2 squared over 0.4 squared is exactly 4. I get m is equal to exactly 4 kilograms. And they asked for the weight of the bananas in newtons, so multiply by g. 4 times 9.8 is going to be 39.2. mg is equal to 39.2 newtons. And I know that 4 times 9.8 is 39.2 because I've been doing physics for way too long. Okay, now that is done, we can finally talk about the simple pendulum. So that'll be our next topic. Excellent. If this sheet is ready to go. The simple pendulum. This one is going to require a bit of a leap in logic for you Physics 1 students, and even for some of you calculus students. Unless you're in Calculus BC and you've learned about Taylor series, you might not find some of this to be very convincing, but I will try to convince you that there is some truth to this. So, for a simple pendulum, what makes a pendulum simple, you might ask? A simple pendulum would be a pendulum for which all of the mass is tied to the end of a string, and the string is considered to have negligible mass. This is opposed to something that we will talk about next time, known as a physical pendulum, which is when you have literally anything else swinging back and forth that is not as simple as this is usually called a bob or a plumb bob attached to a string. So if I swing my favorite physics demonstration, apparently, this ruler, if I were to swing this around back and forth, if I were to hang it by sticking something through it over here and just let it swing back and forth, will it even get captured on the camera? I don't know. Yeah, if I let it do that, then that is what we would call a physical pendulum, not a simple pendulum. If I were to swing something, I'll say my calculator, if I were to hold it over here and just let it swing back and forth, that's another example of a physical pendulum. We'll talk about physical pendulums in more detail next time. But for now, our focus will be on the simple pendulum. So for the simple pendulum, let's figure out if it meets the requirements for simple harmonic motion. Is there a restoring force when this thing starts swinging back and forth? Well, there is something pulling it back towards some sort of central position over here. And it swings back and forth between two extreme positions. It seems like it could be simple harmonic motion. So how would I define the displacement? In this case, I would define the displacement in terms of the angle in radians. I would call my displacement theta. I would just use my angular displacement here. And as for my restoring force, well, what forces are going to be acting on this thing? This thing is going to have a force of tension acting on it this way, and a force of gravity acting straight down on it. And the force of tension is going to end up canceling out, is going to have to cancel out with a component of the force of gravity. So what we're going to do is we're going to create a coordinate system where one axis is going to be tangent to this path that the mass is moving on, at least at this current instant in time. And then our other axis is going to be perpendicular to that. It's going to be parallel to the tension force. And I want to go ahead and break this force of gravity into components along that new coordinate system. So if this angle over here is theta, then that means this angle over here would also have to be theta. The angle between, I guess I didn't draw it very well. I probably should have shifted it down a little further. I'll redraw a copy of it over here. So you've got force of tension this way, and I'll draw force of gravity over here, straight down. And then we had this angle theta over here at some point, so let me draw that line completely vertical. And then we called this angle over here theta. Well, then this angle over here must also be theta. Both of these angles must be the same because it's that same line intersecting a vertical here and intersecting a vertical here. So the angle with the vertical must be the same. Then we can split our force of gravity into a cosine component this way. Force of gravity cosine theta, and a sine component this way. Force of gravity sine theta tangent to the path. Force of gravity cosine theta has to cancel with the force of tension. We know this because we know the direction this thing swings. It seems to be accelerating in a direction that's, well, tangent to the path, with no acceleration towards wherever this pendulum is being tied. No acceleration in that direction and no acceleration in that direction. We don't see any indication that there's acceleration along this axis. We only see acceleration this way. So force of tension, force of gravity, cosine theta must cancel out. So that leaves us with our net force just being force of gravity sine of theta, or mg sine theta. Okay, well, it does point towards this equilibrium position, and if the mass was on the other side and you drew this again, you would have a force of gravity cosine theta pointing this way. So yeah, it seems like it's always going to be opposite to the direction that theta opens. If theta opens to the right, force of gravity cosine theta is going to be down and to the left. If theta opens to the left, then force of gravity sine theta is going to be pointing down and to the right. I think I accidentally said cosine back here. If I did, I meant sine. Force of gravity sine theta points towards the left when you're on the right and towards the right when you're on the left. So it does seem to meet that requirement. It does seem to have the negative sign part of, where did I have it? The negative sign part of what a restoring force should be. It seems to have that. It seems to be opposite in direction to the displacement. I just didn't write the negative sign. Is it proportional to the displacement, though? Is it of the form constant times, in this case my displacement is theta? Well, it doesn't look like it. It looks like it's proportional to sine theta. It's a constant times sine theta. That's not quite the same thing, but you see there's this trick from calculus called the small angle approximation. The small angle approximation. And those of you in Calculus BC who have learned your Taylor series expansions of sine of theta, you already know how this works. But for the rest of you, you're just going to have to believe me when I say, in calculus, you can prove that sine of theta is equal to, this of course requires theta to be in radians in order to work, is equal to theta over 1 factorial minus theta cubed over 3 factorial plus theta to the 5th over 5 factorial minus theta to the 7th over 7 factorial, and these numbers keep on going plus minus forever. And basically the idea is that you would just take, for example, let's say you take the first 4 terms here up to this far, and you would get an approximation of sine of theta, and it would be precise enough to the, you could measure the precision by looking at which of these terms is going to be the smallest value, which would be the last one you took, because theta is typically going to be some sort of decimal, and even if it wasn't, you're dividing it by denominators that are getting bigger and bigger. So as you go further and further to the right here, these terms are getting smaller and smaller, which means that the amount that they could be off by is also getting smaller. Like maybe if you only take one term, you'll be off by a 1/100th, but if you take two terms, the most you'll be off by is like 1/10,000th, and so on and so forth. So you can just keep going to whatever degree of precision you want. You don't need to worry about that. The main idea here is if you choose an angle that's small enough, then you can get it to stay pretty accurate using just the first term of this approximation. You can say sine of theta approximately equals theta for small theta. Well, what's considered small? That depends on who you ask. Some people will say that theta needs to be less than about 15 degrees, or that would be pi over 12 in radians. Some people say that you can get away with theta being less than or equal to 30 degrees, or pi over 6 radians. In case you don't find all this to be very convincing, don't worry, I have something much simpler that you can look at. Those of you who haven't done pre-calculus and trigonometry, I'm sorry, but this is just something that is probably not going to make much sense to you. You might want to try typing sine of theta into a graphing calculator and see what it produces, but the graph of sine of theta, for those of you who've done your trigonometry chapter in pre-calculus, you know that the graph of sine of theta looks like this. So it's got that pattern over there, and then it just kind of waves around like this. And it just goes on repeating this pattern forever and forever in both directions. And we know that this first hump over here occurs at 90 degrees, or pi over 2. And 30 degrees, pi over 6, well, that's 1/3 of the way to 90 degrees. So that's around here. So that's pi over 6. Okay, well, if you look at it, so that's the graph of sine of theta. F of x equals, I guess, yeah, f of x, or f of theta rather, f of theta versus theta. So that's f of theta equals sine of theta. If we look at it just up to pi over 6, it looks kind of linear, doesn't it? Well, what if I were to draw the graph of f of theta equals theta? That would be a straight line that looks like this. Oh, so if I zoom in, of course, there is a gap between them. They're definitely not exactly the same over here, but they're so close to each other that you might find it convincing that, yeah, sine of theta does approximately equal theta, up to around, I would argue, pi over 6. Some people are more strict and would say you probably want to stop at 15 degrees instead. But either way, the point is, as long as you don't pull the pendulum back too much, you can get it to engage in simple harmonic motion. You can get it to be, you can get the restoring force to be of the form constant times displacement. Where was it? This. You can get the restoring force to be of this form. mg times theta. Sine of theta is approximately equal to theta for sufficiently small theta. And I guess to make this extra formal, we would say the restoring force, that component of the gravitational force that's tangent to the path, I guess I'll call it F tangent, is going to be negative mg theta, where the mg basically plays the role of the k in the spring version of the equation. Right? For springs, it was spring force equals negative kx. For the pendulum, it's the component of the gravitational force equals negative mg theta. The mg is basically doing the same thing that the k was doing for springs. All right, so that's it. That's the simple pendulum. So we've fulfilled the first two requirements for simple harmonic motion, which is the negative sign and the fact that this is a constant times the displacement. The third condition is conservation of energy. And is energy conserved here? Absolutely it is, because the force of gravity is a conservative force, so no non-conservative work there. The tension is not conservative, but the tension doesn't do any work. The force of tension is always perpendicular to whichever way the pendulum swings. Whichever way the pendulum moves, wherever its displacement is always perpendicular to the tension force. Force of tension times displacement times cosine of 90 degrees between their directions. That's zero work done by tension. Work non-conservative equals work done by tension equals zero. So mechanical energy is conserved. And there you go. A simple pendulum, as long as you don't pull it too far back to set it in motion, will engage in simple harmonic motion. Now we look at another type of motion that we've seen before that actually has some relation to simple harmonic motion. This is where we're going to be deriving some equations. Uniform circular motion. Let's take a look at uniform circular motion again. So let's say we have an object over here, and it's moving around, and maybe we see it at some other instance, it's over here. And let's take a look at how this thing behaves. So I want to look at this from the perspective of someone looking from under the circle. So let's go ahead and bring back an old friend here. The giant eyeball of physics. The giant eyeball of physics. It is so back. So if the giant eyeball of physics looks at this from very far away, so I guess the way I have it situated, it's actually way too close. But from very, very far away, if the giant eyeball of physics looks at something moving in uniform circular motion from very far away, then it might be far enough away that the eyeball can't tell that the object is moving, along the, I guess, y-axis, and the eyeball will only see the horizontal part of the motion. The eyeball will only see the horizontal part of the motion. Maybe I should have just put the eyeball up here. Yeah, that would work. Is there a way I can... No, it's going to roll away. I would love to just leave it sitting here, but I don't have anything to keep it still, so... I mean, at least I've demonstrated my point, I hope. If we are just looking horizontally, then we might see an object that's moving just between these 2 points. We might see an object that's just moving from here to here. If I try to move, I'll try and do this with both of my hands. If I try to move one hand along the circle and move the other hand in the way that it would look to someone viewing from very far away, then it would look something like this. You see what my bottom hand is doing? It's just going back and forth like an oscillating object on a spring, for example. Yes, seeing the connection? Well, we can demonstrate this connection mathematically. We can demonstrate mathematically that if you just look at a component of the motion of something that's in uniform circular motion, then at least for that component, if you're just looking at it from purely the motion in x or purely the motion in y, then it does actually behave exactly like simple harmonic motion. Only difference is that there's a second dimension to this type of motion that you kind of have to neglect in order to treat it as simple harmonic motion. So here's what we can do. This object, if it's going to be in uniform circular motion, let me choose a darker color for this, is going to have some sort of tangential velocity, right? Some constant speed. The tangential velocity is going to change direction, but not magnitude. So that's your v tangential over there. And let's see. Of course, it's also going to have a centripetal acceleration pointing towards the center at any given time. So that's your a centripetal. And you're going to have this this pink distance over here is just the radius r. Let me actually write it in pink. So that's r, just the radius of the turn. So I want to define the position, the velocity, and the acceleration in terms of x. So I want to define x. I want to define vx. And I want to define acceleration in x, which ultimately will allow me to define the force in the x direction, the horizontal component of the centripetal force. That's what I want. I just want to get all of these horizontal quantities. Okay, so if this thing is going to behave like simple harmonic motion, then I would say that the distance from here to here would be an amplitude, right? X max, which is equal to how much? Well, it's equal to this distance over here, which is the radius. Okay, so maybe we can define x max in terms of the radius at all other points besides this extreme over here. If I were to drop a perpendicular over here and define an angle theta, I guess I would define this as my theta. I don't have enough space to even write the theta without it looking too messy, but I guess I will just arrow to it and say theta there. So I would then say that x is simply going to be r times, it looks like cosine of theta, right? This over here would be x for this moment in time. This x is equal to, I drew my arrow in the worst place possible, didn't I? X equals r times cosine of theta. Simple enough, right? You've got a right triangle over here, hypotenuse is r, and I just want the horizontal part, the x, it's just equal to the hypotenuse times cosine theta. We've seen this hundreds of times by this point. Well, maybe not necessarily hundreds. I guess that depends on how many problems you practiced. It ought to be hundreds, I would hope so. But I can definitely see people who've only seen it maybe closer to like 60-ish times. That's just a ballpark estimate. Anyway, so we got x is equal to r cosine of theta. That's all good. Now let's try and define Vx. So x is just going to be equal to r times cosine of theta at any given point, where theta equals 0 at the beginning over here, where you start, I guess, at x equals its maximum value of r, and just theta just opens and increases from there. Vx is next, so the x component of the tangential velocity. Well, I guess I would have to draw a horizontal line over here and make another right triangle, so I guess I'm going to have to draw a vertical line as well. And let's see. Which of these angles would be equivalent to this theta over here? Let's see, so the tangential velocity, well, it's always going to be, V tangential is going to be 90 degrees ahead of r. V tangential is going to be 90 degrees ahead of r at all times because it makes a 90-degree angle with r. Let me see. I mean, my gut is telling me this angle up here is going to be the theta, but I'm trying to look for something more definitive here to give you guys. So if that's theta, then this angle over here also has to be theta because you've got two horizontal lines. You've got these two horizontal lines, and then you've got this one line, the radius, intersecting both of those parallel horizontal lines. So you would just have these opposite interior angles, which would have to be equal. So this angle over here has to be theta, and because r makes a 90-degree angle with V tangential, that means that tiny angle over there, let me just redraw this. Let me redraw this over to the side and make it extra clear. So you have R, and then you have this theta, and then you have V tangential looking like this. And if this is theta, then this must also be theta, which means that this must be 90 minus theta. And over here we have a vertical, so that's 90 degrees. If this is 90 minus theta, then this is 90 minus theta, which means this is theta. There we go. And then that would mean that the x component of V tangential, or Vx as I called it, is going to be this side over here, which is opposite of theta. So it's going to be V tangential times sine of theta. So Vx is equal to V tangential sine of theta. And actually, the other thing is it looks like it's going to be in the opposite direction to x, so I would probably want to throw in a negative sign here, but we're not going to worry about that for now. That'll become relevant next time. We won't worry about it for now, but you could toss in a negative sign over here. Actually, you know what? Fine, I'll include it. Negative V tangential sine theta is your Vx. Okay, perfect. Next, finding the x component of the centripetal acceleration. Finding the x component of the centripetal acceleration. Well, the centripetal acceleration points towards the center, and as luck would have it, it points exactly opposite to the direction of R. Well, I guess R doesn't really have a direction, but I think of it as going from the center to the edge of the circle. But yeah, a centripetal has this direction, and to get its horizontal component, well, I'm in luck. I've already drawn the theta for it, so here's the horizontal component of a centripetal. If I make a right triangle, then this angle over here is just theta. I guess, let me redraw again. There's a centripetal, drew it a little bit bigger. This angle we already showed is theta. So if I drop a perpendicular here and make a right triangle, then this over here, AX, is just going to be the adjacent or cosine component for this triangle. So AX is going to be a centripetal times cosine of theta, and it's opposite in direction to x, right? X is to the right of the center, but a centripetal, its x component is to the left. So let's put in a negative sign there. Okay, and then force is going to be easy. The x component of the centripetal force is, well, centripetal force is mass times centripetal acceleration, so the x component of centripetal force is simply mass times the x component of centripetal acceleration. Did I say that right? The x component of centripetal force is mass times the x component of centripetal acceleration. just in case I said it wrong, I said it again, this time correctly. So that's going to be equal to negative m acentripetal cosine of theta. All right, wonderful. So we have our force in the x direction. Does this force act as a restoring force? Is it proportional to x? And is it opposite in direction to x? Well, if I look at r cosine theta over here, let's rewrite acentripetal. Centripetal acceleration is equal to v squared over r, v tangential squared over r. But it's also equal to something else, right? We learned in rotational dynamics that v tangential can be written as r times omega, the angular speed. So v tangential squared would be r squared omega squared. And if I put r squared omega squared over in the numerator, one of the r's will cancel out with the denominator, so we get acentripetal is also equal to r times omega squared. Okay, let's see what that does for us here. So we get negative m r omega squared cosine theta. Oh, wait a minute. R cosine theta, that's x. So this is negative m omega squared times x. We have it. M, the mass, is going to be constant. Omega squared, the angular speed, must be constant because the magnitude of the tangential velocity is constant. By definition, that's how it's supposed to work with uniform circular motion. So, yes, if we just look at one dimension of an object in uniform circular motion, we do see actual simple harmonic motion. We do actually see simple harmonic motion here. How do you like that? Now then, we can do a little bit more here. Let's derive some equations. There are some equations we can derive, and once we have them derived, we will maybe look at a quick problem or two and then wrap up with that. Actually, I'm not sure if I want to do problems with those equations. I might want to save it for next time. Well, we'll see once we get there. So now what I want to do is try and define some concepts that we did look at for uniform circular motion and see if we can use those concepts for simple harmonic motion. The concepts I'm referring to are period and frequency. I think we dealt more with period than frequency, but I'm pretty sure I mentioned frequency at the very least. So for uniform circular motion, we said period was the amount of time it takes to complete one full round around the circular path, one full cycle. And that definition still remains true here, right? The amount of time it takes to circle once is also the amount of time for the simple harmonic motion that we see from a faraway distance to occur once, to cycle once. So we're trying to find the period for that, for any object really in simple harmonic motion, taking inspiration from uniform circular motion. So we said what? The speed, the magnitude of v tangential, we said, was equal to 2 pi r, the distance, divided by the time, and you travel a distance of 2 pi r in a time that we define as 1 period, 1 full cycle. That's what we said. And then we took this equation and rearranged it, and we multiplied the t over to the left, we divided the v over to the right, and we got t equals 2 pi r over v tangential. The time it takes to circle around once is equal to the circumference of the circle, the total distance, divided by how quickly you are traveling along the circle. Distance divided by speed equals time. Okay, nice. But we can repurpose this, or rather, we can rewrite this now in terms of something new. What is r over v tangential? Well, let's look back over here. V tangential over r is omega, so if we flip it upside down, r over v tangential is 1 over omega. Or better yet, I would just write it as just 2 pi over omega like this. Okay, 2 pi over omega. Frequency is going to be the reciprocal of period. So frequency is equal to 1 over period. If I were to do 1 over period over here, frequency is equal to omega over 2 pi. Frequency is the number of cycles per second. So period is the number of seconds it takes to complete a cycle, a repetition of something. Frequency is the inverse of that. It's the number of repetitions that occur within a given amount of time, typically a second. It's going to be in units of 1 over seconds, or it's often written as seconds to the negative 1, or also the hertz, Hz. I know I've mentioned this in previous lessons. I just can't remember off the top of my head when. But just in case you've forgotten, that's what frequency is. The standard unit for frequency is the hertz, or the 1 over a second. Cycles per second if you really aren't comfortable writing a 1 over seconds. But cycles are not a real unit, kind of like radians. Whatever you multiply them by, they're kind of like blank units that get replaced immediately by whatever real units you multiply them into. Cycles, repetitions, oscillations per second, whatever you want to call them. Something you can put in the numerator over seconds, that's frequency. Okay, can we find another definition for this omega, another mathematical definition? Well, how did we get this omega to begin with? So it was 2 pi r over v tangential. Let me see, where did we get that from? I had this all thought out earlier, but it's now just completely evaporated from my mind for some reason. Where did we get this from? Let me backtrack a little bit. So specifically, I want to find this r over v thing. and see how it relates to this. Let me see. Fx is equal to negative m omega squared x. So if I divide back by m, that would tell me then that my acceleration, that would allow me to redefine acceleration. Ax equals negative, if I take the force divided by m, it's going to be negative omega squared times x no, that's not what I did before. What did I do before? Why am I blanking on this? Let me look at my notes. Give me a second here. So we did mass times centripetal acceleration times cosine of theta equals some constant times r times cosine theta Let me see. So, I guess what I want, because I didn't do things exactly like my notes here, so replicating it would. So I did mass times acceleration times cosine of theta, and then I said it's equal to some constant times r cosine theta. That constant being m omega squared. Okay, so I think what I can do then is I can say this is of the form negative beta times x, where beta is equal to m omega squared. So then the negatives cancel out, and I can do beta equals m omega squared. Beta is equal to m omega squared. And if I divide by m, then I get omega squared equals beta over m. And if I take the square root of that, then I get omega equals the square root of beta over m. Okay. Okay, so these two results, I'm going to now use to define this omega for the spring case and the simple pendulum case. That's what I'm going to do. So for the simple pendulum, beta is this constant in front of the theta is going to be mg, and for the mass attached to a spring, beta is just going to be the spring constant k. Actually, will that even work for a spring? Or not a spring, rather, for a simple pendulum. I didn't think that far ahead. Oh well, we'll deal with it when we get to it. So let me grab, yeah, we need a new sheet of paper. And let's go back to the spring. So for a spring, we said F spring is equal to negative kx. So this tells us then that the beta for a spring equals k, which tells us then that omega for a spring, by the way, this omega is called angular frequency. And the reason for that is because, well, you get it by multiplying. If I rearrange this equation over here, which is something I probably should have done earlier, if you multiply the 2 pi over to the left-hand side, then you can get omega is equal to 2 pi times f. 2 pi times f. And if the frequency is just cycles per second, and you multiply by 2 pi to get omega, which is going to be in radians per second, then basically these 2 pi, this 2 pi comes in radians, is the way you can think about it. You're basically taking frequency units and just converting their numerator into radians. So it's sort of like this new kind of rotational version of frequency that we call angular frequency. At least that's my reasoning behind the name. It makes sense to me, but if you have your own way of reasoning through the name for it, then by all means go with whatever makes sense to you, as long as it helps you remember the name angular frequency. So omega for a spring is, so omega is square root of beta over m equals square root of beta spring over m is equal to square root of k over m. All right. This allows us to write down the frequency and period of a mass attached to a spring. Frequency for a mass spring system is equal to omega over 2 pi omega over 2 pi is equal to 1 over 2 pi times the square root of let's see, omega was equal to the square root of k over m. And if I want to define the period for a spring, I can just do 1 over the frequency, or 2 pi over omega, however you want to look at it. 2 pi over omega is equal to 2 pi times 1 over the square root of k over m is the square root of m over k. Okay, these you're going to want to remember. Honestly, you only need to remember one of them, and then just remember that the other one is just the reciprocal of the first. So these are relationships worth remembering. These two and what we had earlier with period equals 2 pi omega, this is worth remembering, or its reciprocal, frequency equals omega over 2 pi, or what I would rather have you do. Multiplication is easier to remember than division, because with division you have to remember what is being divided by what, whereas with multiplication you don't have to remember the order. So the one I would recommend the most, the easiest, would be this: omega equals 2 pi f, and then work from there. Anyway, that is for a spring. What about for a pendulum? Now, I'm not entirely sure this is going to work. I feel like I'm forgetting something in the pendulum case, because I don't have anything involving... I know the final equation is supposed to have the length of the string involved, and I think I know where it's going to come from. Oh, I think I know where it's going to come from. So, the length of the string is going to be baked into this theta. I can redefine theta as in terms of arc length. Yeah, that's going to be it, isn't it? Okay. The restoring force for a pendulum, which I called F tangent, equals negative mg theta, equals negative mg theta, and theta times r is equal to s, right? Well, I guess I don't need the arrowhead there. S is equal to r theta. We learned that in the previous chapter. And r, in the case of the pendulum, if this is part of some sort of circular path, the radius of that circle is just going to be the length of the pendulum string, which I will call L, lowercase l, or capital L. I guess it depends on which textbook you're using. Some textbooks use lowercase, some use uppercase, and I learned from one of my students earlier this week that apparently some textbooks also use H, because that's not confusing at all. We don't use it for anything else. Nope, can't think of anything else that H is used for that could potentially cause confusion. And of course, I'm being sarcastic again. Where was I? Right, so instead of R for the pendulum, for the radius of my arc is going to be L. So I'm going to say S is equal to L times theta, and if I divide both sides by L, then S, or theta, is equal to S over L. So this is going to be negative mg over L times S. Okay, here we go. And that tells me then that beta of the pendulum, the constant part of the pendulum restoring force is mg over L. And then if I apply similar reasoning, that tells me that omega for a pendulum, the angular frequency for a pendulum, is square root of beta pendulum over m equals the square root of mg over L over m. The m's cancel out, and so I get the square root of g over L. There we go. And we can now define the frequency and period for a spring, for a pendulum rather, F for a pendulum, a simple pendulum, mind you. F pendulum is going to be omega over 2 pi. Omega pendulum is square root g over L over 2 pi, so that's 1 over 2 pi times the square root of g over L. And period will just be the reciprocal of that. Equals 2 pi over omega equals 2 pi times the square root of L over g. And these, just like these, commit to memorizing one of them and know that the other is the reciprocal of the first. The one I would recommend memorizing is the period one, because it doesn't have as many fractions in it. You don't have to remember that it's 1 over 2 pi. Plus period tends to be asked for more often than frequency is what I've found, at least in my experience. I could be wrong. I might just be remembering problems asking for period more vividly than the ones asking for frequency. It might just be a cognitive illusion of mine. But period feels like it tends to be more relevant. And also the other thing about period is if you line up these period equations, if you line them up, two pi square root L over G in the pendulum case, or 2 pi square root m over k, I have this nice way to remember what's in the numerator and what's in the denominator, because it's very, very easy to get these mixed up. Is it L over G or G over L? Is it M over K or K over M? You will be asking yourself that constantly, but once upon a time, I just kind of on the spot, when working with this one student, came up with a way to remember the numerators. If you write it like this, T, L, M, you just read the numerators, T, L, M. That spells tellum. If your classmates are having trouble remembering what the numerators are in your period equations, just tell them about tellum. Or if you read it backwards, you could also say it reads melt. Maybe that's easier to remember for some of you, but I think the tellum story is funnier. So yeah, tellum. About tellum. Thank you. I'll be here all day. Imagine your AP exam grade being saved by none other than a very bad dad joke. Okay, so I think that is it for today. I don't know if I want to... Do I want to do a problem or two using these? Or should I save it for next time? Well, we're already over 3 hours in, so I feel like calling it quits. Let me see if there's like a quick one that we could do. There was a really good one that I did with a student the other day. Hold on. Let me see if I can dig it up. Actually, let me see how far we can go with this one. I feel like we don't have enough to actually do this one yet, at least not fully, but let's try and see how far we can go. So it says an oscillator consists of a block of mass 512 grams connected to a spring. So spring doesn't matter if we draw it horizontally or vertically. I know I haven't proved that very well today, but I'll come back with a better proof next time. So 512 grams is the mass. M equals 0.512 in kilograms. When set into oscillation with amplitude 34.7 centimeters, amplitude is 0.347 if converted to meters. It is observed to repeat its motion every 0.484 seconds. Part A, find the period. Well, that should be pretty obvious if you're just paying attention to the problem. It said it repeats its motion every 0.484 seconds, so that must be the period. Oh, and I just remembered there's one more thing to check with these equations. Do the units actually work out? That's something we need to look at. We only need to check one of them, because if the units come out to be seconds for period, then you know they're going to be inverse seconds for frequency. So yeah, I'm just going to check this one, and check this one. Just got to remember to do that and see that the units do indeed come out in seconds. Anyway, so period was found. Part B, find the frequency. Okay, frequency is just 1 over the period. You all know how to do 1 divided by 0.484 on your calculators, so I'm not going to take the time to actually do that. Part C, find the angular frequency. Angular frequency. Well, we can just do 2 pi f would be the quickest way, right? Angular frequency equals 2 pi f. Two pi f, which means 2 pi times f is 1 over the 0.484. And again, that's something you can plug into your calculator and find easily. You don't need me to do that for you. Part D, find the force constant. Part D, find the force constant. Okay, well, we know the mass, and we know the period. We can find the force constant. Actually, even if you didn't know the period, if you knew period or frequency or angular frequency, if you knew any one of these three, they all have some relationship with m and k. They all have some relationship with m and k. The angular frequency is the square root of k over m. The ordinary frequency, for lack of a better term, is 1 over 2 pi times the square root of k over m. And the period is 2 pi times the square root of m over k. So whichever of those three you want to use, you do have some connection to m and k. You know m, and you know at least one of these three. In fact, we know all of them, so you can solve for k. You're just going to have to do things like squaring both sides to open up the square root and whatnot. So let's see. I'll just use the period equation. So I would do 0.484 equals 2 pi square root m over k. Divide by 2 pi, square both sides, cross multiply. Okay, I'll actually do this one. So it would be t, I said divide by 2 pi, so t over 2 pi equals square root m over k. Since we're solving for k, I might as well just flip it. 2 pi over t equals square root k over m. Square both sides, I get 4 pi squared over t squared equals k over m. Multiply the m over, and k equals 4 pi squared m over t squared. You know m is 0.512, you know t is 0.484. Don't forget to square it. Plug in those numbers and get k. Again, you don't need me to do that for you. So that was the force constant. Part E, find the maximum speed. Well, we can do that now that we have k from the previous part, and we know the amplitude. So we can calculate 1/2 ka squared, the maximum potential energy, which is also equal to the maximum kinetic energy. And we set that equal to 1/2 mv max squared, multiply by 2, divide by m, and take the square root, and you're done there. 1/2 mv max squared is equal to 1/2 ka squared. In fact, we can just cancel the 1/2 up front. V max squared equals k times a squared over m. Plug in the k that you got from the previous part. Plug in the a squared that was given. Well, a was given, but you know what I mean. And divide by the mass, which was also one of our givens, and take the square root, and you're done. So V max equals the square root of, oh, would you look at that? Square root of k over m times a outside of the square root. Square root of k over m, that's omega. So we could have just done omega times a to get V max. How about that? This is what I mean, or what I meant rather, at the beginning when I said you just get overwhelmed with options. You see this, and then you just sort of develop tunnel vision, and you go, oh, I should remember this because it looks like a very convenient shortcut. I don't know. I mean, how many steps are we actually saving? I think it's more worth it to just master doing it without having to remember shortcuts like this, because you've already got enough new stuff to memorize as it is. You don't want to overwhelm yourself with all this extra stuff. Like, this is stuff that you leave until after you've studied every single thing possible and you can't find a single thing that you need to review. This is extra. I wouldn't put this at the top of the priority list. You will do just fine without this shortcut. And besides, there's going to be another equation that we're going to see next time that gives you this with a little bit less hassle. Oh yeah, we will see amplitude multiplied by omega again. We will see it. And final part of this question says, find the maximum force exerted on the block. Okay, well that's easy. Force max is equal to K times the amplitude. And next time we'll see that this also has another equation involving omega. In fact, you might be able to see it right now. Think of it, if you think of it as F max equals m times acceleration max, what is acceleration max? I might as well give you this now, just so you have something to sleep on. Acceleration max is equal to F max over m is equal to Ka over m. Wait a minute, K over m? The square root of K over m is omega, so K over m is omega squared. Ah! And there you go, yet another shortcut equation that I don't actually encourage you to memorize just yet. Save it as something extra for later. Anyway, I think this is where I will wrap things up. So, in order to drill these relationships into your head and really get quicker with the algebra that these equations will have you doing, go to the course plan, linked in the description. I showed it earlier. Let me put it up on screen and show it to you again. For homework, I want you to go to the Simple Harmonic Motion tab and scroll down over to this Simple Harmonic Motion worksheet. And yeah, it's a lot of drills, but they're actually really quick. The first couple might be head scratchers, but then you'll get into a rhythm, you'll get into a routine, and it'll start making sense from there. First sheet is just rearranging equations that should look familiar now that we've seen the period and frequency equations for pendulums and springs. Then you've got just using the definitions of period and frequency over here. And this does have an answer key at the bottom, so you can always check your work. Then it's got a dedicated pendulum section and a dedicated spring section. And yeah, it's 139 questions, but they're all really easy questions. They're mostly just quick drills. The first few of each section might require a bit of thinking just because you're, shifting topics. But once you've done a couple problems from each section, the rest of them you'll be able to blow through. At least that is the hope. Through repetition, you just start to develop good mental habits that will carry you through these problems and make it that much easier for you to focus on, the understanding part of the tougher problems that you'll see in textbooks, on the AP exam, and so on. Speaking of textbooks, the questions from the OpenStax textbook, which is linked at the top right here. If you don't have the OpenStax book, this is where you can go get it. If you want to look at some of the questions in there, we haven't covered everything yet, so anything that asks you to calculate what is the position, velocity, or acceleration of an oscillating object at time t equals some number, skip those. We haven't done that yet, so yeah, that is what I would recommend for homework. I'm not going to give you a problem like I usually do here. Just go out there, do that simple harmonic motion worksheet, and look for problems in your textbook. If you don't have one, use the OpenStax textbook. These were the ones that I picked out, but it's been a while since I picked them out, so I don't remember necessarily what my reasoning was in picking them. But I would hope that past me did a decent job picking relevant problems for you to try. And I think that will be it for me. Feel free to post questions and stuff in the comments. I'm going to reevaluate that one proof that I failed at today and make sure that I can do it properly next time. And yeah, that's it. Have a good one. Class dismissed. I will see you next time.